Hey, how's everyone doing? Hey, how's everyone doing? Please drop in the chat where you're calling in from. Oh, hey, so many London, Atlanta, California, Kenya. Amazing. Okay, one second. Cool. So I was echoing because Saad and I are actually in the same room right now. Saad is going to be starting real quick, but let me take up my background. I'm actually in the Kleebird office. So as some of you may know, Saad is the co-founder and CEO of Kleebird. They were in the latest YC batch, and they were actually able to raise a funding round of $4 million. So they're doing amazing stuff, and Saad has put in a lot of time into preparing this workshop for you all, where we're actually going to be building a very simple kind of neural network model to basically generate text in a way that's similar to a GPT model. Saad is about to join us right now and looking forward to getting started.
Hey folks, can everyone hear me?
Yeah, it's enough your volume. Okay.
Awesome. I'm going to turn on. Yes. Okay. Perfect. Um, okay. Perfect. How's everyone doing today? Really excited to go through lecture number three. Can I get a yes in the chat one more time? Everyone can see my screen and hear me, right? Yes. Okay, perfect. Sweet. Yeah, let's go ahead and jump into it. This one is going to be probably an hour and a half. I'll try to keep it to it, but super excited to kind of get started. For those of you who are new, let me kind of explain what's going on here. And of course, for our returning customers, you'll understand very well that we are going through Andre Karpathy's Zero to Hero series, and our goal is basically over the course of the past couple of weeks, and after maybe like one or two lectures, we're going to build up the intuition, the reasoning, the fundamental knowledge to be able to build our own GPT model from scratch. Now, we're not going to do that today. We didn't do that last week. Our first week, for example, we built an autograd engine, which is basically capable of doing mathematical operations and then calculating the gradients of those operations and then doing back propagation. So this was critical in, for example, building our first neural net. Last week, we learned about softmax, we learned about log likelihood, and we actually built our first language model. Does anyone remember the name of the first language model that we built? Bigram, awesome. A bigram model, basically, if you guys remember, I'm going to open up my directory here. On the Head Starter page, you guys will see this as well. But on my side, and again, guys, remember, as we go through this, I'm going to make a warning again. Don't worry so much about implementing the code alongside me. You guys will get the chance to do that yourselves on your own afterwards. But just watch me and make sure you understand what's going on. But, last time we did character level language modeling, where we had this data set that basically had a bunch of words. And we were trying to build a model that would make more. This data set has a bunch of names, right? And it has names like Emma, Olivia, Ava, Isabella, basically all the most like common baby names in America, right? And we were trying to make a model that would predict more names from scratch. And again, this is just a bit of review here. One thing that we realized that's really helpful is counting, right? So for example, if we go through all of the element-wise pairs in the data set, right? So if I take, for example, the name Olivia, right? So OL, how many times did that show up? LI, how many times did that show up? VI, and so on and so on. We basically constructed these bigrams. We counted in this chart how many times pairs of letters show up. We made sure that we had these start and end tokens. That way we knew, for example, when the first letter or the last letter was. And then finally, we basically turned this into a probability distribution. And if you guys remember last time, we went all the way and we actually, these are our bigrams over here. These are the probabilities that we were predicting. We ended up making a model that would use these probabilities to predict new names from scratch. And if I can grab, I had put it down here somewhere. I think like it was really funny last time that the first word that we had predicted as a name was sexy, if you guys remember that. There we go. See these five names right here? Sexy, Moma, Surel, Azitin, Konamitan, whatever, right? And we remember last time that the names that we're predicting are pretty bad. And the reason these are so bad is because, as we had mentioned last time, a bigram language model just takes a look at two tokens at a time. In this case, the tokens are just characters. So if I'm just looking at like one character as my context, remember, context is a word that describes the amount of information that a model has access to at a time. If my context is only one token, and based off of that, I'm trying to predict the next token, it's really difficult to actually make a whole name because it actually matters. Is the letter that I'm looking at, is it the first letter? Are we like 5 letters deep? Are we 10 letters deep? Right? So sometimes we end up with these names that are like really awkwardly sized, either too long or too short, right? So we came to this conclusion that we want in the future to not just do bigram modeling, but we want to do trigram, quadgram, pentagram, right? We want to be able to have our model have more and more context and look at not just the given character that we are at and what the next character is, but what are all the previous characters that we've seen so far. And we made the decision that, it was just going to be too unruly to kind of do this, in a counting method. It would be too difficult. So we wanted to train a neural net. There's just one thing I wanted to show from last time, if you guys remember. These were the names that we predicted, right? Like sexy, Moma Soraya Lezitin, Konimetan. These sound pretty terrible. But if you guys remember, I had also tried the uniform distribution. And I wanted to show you guys the names that we got out there to prove to you that yes, the names that we predicted last time were bad, but the uniform distribution is a lot worse. So let me just search that up. See right here, these words right here, these look nothing like names. So at least we can say that our bigram model is bad, but it is certainly an improvement over the uniform distribution. How do we do that mathematically? We came up with a loss function last time. Our loss function was log likelihood, and we proved that the uniform distribution has a really bad log likelihood, and our bigram model is slightly better. Okay, perfect. So that's just kind of review on like where we're at so far. And Faizan is going to be working alongside me, and I'm going to be kind of asking him questions. He's going to be interrupting us as well. He'll be interrupting me as well to kind of ask questions, stuff like that. And Fazan, since you're in the same room with me and my mic is on, you can just turn and ask me any questions. Okay. Fazan, do you have the Head Starter page open? And can we go ahead and um, get started?
Yeah. Um, well, actually, can the folks hear me? Saad and I are like 10 feet apart, so I want to just make sure people can hear me.
Yes, everyone can
Okay,
hear you.
cool. So a lot of folks are asking for the links and code to the workshops from the last 2 weeks or the last two workshops. So there, I shared two links already in the chat. So uh, these, if you go on the headstart.co/workshops, that'll take you to the recordings of the previous two lectures. And then when you click on Open Notebook on one of the recordings, it takes you to this link, which I'll share in the chat again, which will take you to the interactive page where it's basically a Jupyter Notebook environment. Let me actually share my screen.
Yeah, I'll stop sharing.
Cool. So this is the Jupyter Notebook environment that you all can follow along this lecture with. So I know, like, for the previous lectures, some folks got kind of lost. They weren't able to copy code, kind of like in time, or they want to reference like the completed code. So now we have that all for you available here. So in this kind of repo, you see we have lecture three complete. If you want to just follow along with Saad, like go as he code along with him, then you can just do that here in lecture 3.ipynb. If you want to view the completed code, you can just do that here. And once we're done with this workshop, we're gonna upload the recording here, and then you can kind of watch the workshop as you code along. So I was able to build this, and during this lecture as well, we're gonna be implementing aspects of this paper, neural probabilistic language model. And so I have, implemented easy access to read that paper here. And if you have any questions from the paper, you can just highlight any part of it and get an explanation here. So, basically at Headstart, we're building a new kind of coding environment that lets you, uh, collaborate and compete with AI in certain ways. So hope you all kind of enjoy working with this platform, and please share any feedback after as well. So hope this all makes sense.
Awesome.
Please share in the chat if you have any questions.
Perfect. And Faizan, going forward, whenever you want to say something, I'll just mute my mic and you can unmute yours. All right. That way the
Okay,
audio is perfect.
sure.
Excellent. Is everyone good to get started then? Can I get a ready in the chat? Everyone has their IPython loaded up. We're kind of good to go. Okay, awesome. All right, I'm going to begin one more time with the disclaimer, which is that everything that I share, it's not entirely necessary that you implement it yourself live with me, right? Like I'm reading a lot of like stupid coding about like, graphing on like matplotlib. That's not really that exciting or interesting. What's more important is that you understand the concepts and you deeply digest what we're doing. And then going forward, you can kind of code this up from scratch on your own, right? So please, please, please do not spam the chat with, oh, this line isn't working, that line isn't working. You have the completed code in front of you for that reason that Faizan gave you. Spam the chat with questions, right? Like, why bigram models? Or why did you pick that number for the dimensionality? Or, hey, Saad, what's going to happen when we try to train this model on multiple machines or stuff like that, right? So let's jump right into it. All right, so last time we implemented a bigram model, and we implemented it with a simple neural network with a single linear layer. We took the counts, we normalized them into probabilities, and we basically ended up with that table that I showed you last time that is 27 by 27. Why is it 27 by 27? Well, there's 27 letters in the English language. Actually, technically it's 28 by 28 because we have that start/end special character. But it's 28 by 28 because, 27 letters in the English alphabet, one of the special tokens, and then we have to do a two-dimensional matrix because we're looking at two letters at a time. So that first dimension, our rows, indexes us into the first letter. So for example, the 27th row will be for Z, right? And then, for example, the 27th column would be for ZZ, right? So each additional dimension is taking us from our, first token and then the next token that we're trying to predict. Now, obviously, what you'll realize here is that if we want to take more context into account, the lookup table is going to grow exponentially with the length of the context, right? So one character of context is a bigram. We need 27 by 27, 27 letters of input, 27 letters of output. And then if we have two characters of context, we have to have like this cube shape, right? Because we have 27 for the first letter, 27 for the second letter, and then finally another 27, that third dimension for, what's it called? The actual output token. And again, three characters is 27 to the four characters, 27 to the five. You can see this is going to really explode our memory, right? So we want to make sure that we're not doing this. We're not building these like crazy giant count tables. Rather, we want a neural net that can kind of like generalize. And what we're going to do is we're going to implement in today's paper, in today's lecture, a paper by Yoshia Bengio. He's like one of the greats of natural language processing. This is a paper from 2003. It's really interesting, and I recommend after we implement it today that you guys go through and do it yourself. And that we actually read this paper top to bottom because back in 2003, he's talking a lot about the same problems that we're seeing today. Context windows filling up, parallel processing being too slow. And it's super interesting to see him talk about, word embeddings back in 2003 when GPUs, the transformer, none of this really existed yet. All right. And people are asking a bit more, Faizan in the chat about the Jupyter notebook. If you could answer that really quickly. I want to mention one key point about this paper, which is he introduces this concept of word embedding. So if you guys remember last time, the way that we were representing our words was something called one-hot encoding, right? So for example, for us, our vocabulary size is basically a bunch of vectors that are 27 elements in length, right? Except one of them is going to be a one and everything else is going to be a zero. So if, for example, this was one of our characters, right? If I set s of zero, let's say to one, right? This right here is a vector that represents a single character in our data set. I guess technically, yeah, it should be 28, let's say, right? Wait, I'm so sorry. There's 26 characters in the English language. My bad, my bad, my bad. I've been doing that wrong. So you see right here, this, for example, would represent the letter the special token, right? If I did, for example, if I set 26 equal to 1, this is the vector for the letter Z, right? So these are what we called one-hot encoded vectors. Now, as you can imagine, if we have a larger and larger vocabulary size, right? Let's say, for example, we're not dealing with the 26 characters in the English language, but we're trying to build, I don't know, like chatbots. And the number of words in the English language are probably at least like 200 to 500,000. In this paper, he keeps his vocabulary size at 17,000. You can imagine if we have all these different one-hot encoded vectors, we're going to witness the curse of dimensionality, which basically means it's really difficult for a model to understand what is going on when the dimension size is so high. Particularly, all of these vectors are completely orthogonal to each other. If you remember what that means from linear algebra, then you know what that means. If you don't, just trust me. And what that means is that if the model is, for example, trying to predict a sentence like "the cat is walking in the bedroom," right? And let's say, for example, we see that in training time. So right here, the cat is walking in the bedroom. Let's say at test time, we see a dog was running in a room. If we were to try to train a model that was trained on the cat is walking in the bedroom and then predict this, the model has a really difficult time. And obviously that's the case because every word in this sentence is distinct from every word in this sentence. So right, so right, I've put the pairs right here. So the cat is walking in the bedroom, a dog was running the room. Basically, every single pair is different except for in right here. And one more problem for us is that if our vocabulary of English words is like, these 17,000 words, the cat is walking, whatever, and each word is distinct, any information that we learn about one word does not generalize to other words. So the problem here is that if in our training set we see the cat is walking in the bedroom, and in our test time we see a sequence of words like a dog was running in a room, we're out of the distribution. We actually have never seen this sequence of words before. Our model is unable to generalize, even though any, human can understand that these two sentences are almost the same thing. They're very syntactically similar, right? The grammar is almost identical, and they're very semantically similar. The and or cat and dog, or bedroom and room, even though they are distinct words and they would get distinct vectors when we did one-hot encoding, they're actually really similar. So that's why I'm going to introduce this concept of word embedding. But before I do, Fizan, is that kind of clear so far that like we need a model that can understand more than just, individual words are separate from other words? It needs to be able to relate the meanings of words kind of together. Does that make sense?
That makes sense.
Okay, so here's how we're going to do that. Previously, we were storing our word embeddings, previously it was just characters, as these one-hot encoded vectors. Now, like I said, the problem is that when everything is one-hot encoded, mathematically, it's all orthogonal. Everything is so different, and distinct. We actually need to bring these points closer together. So let's talk about word embeddings. When you use ChatGPT or when you use Claude, the first thing that happens, and this is still the case today, is it takes the words that you have and it does a lookup. There's these lookup tables that are called word embeddings. These word embeddings basically take every word in the English language and they do word to vec. They take in a word and they return a vector. Now, a vector is just a collection of numbers, right? So, for example, if I have like king or queen, it can be like one, two, three. Queen can be four, five, six. You get the point. It's just a collection of numbers. But we want that these vectors have some kind of mathematical shape to them. So, if I go to, for example, the word embedding page on Wikipedia, there's this like really funny graph that says that, okay, let's say the vector for France and the vector for Paris. Let's take the difference between those two. The vector for Germany and the vector for Berlin, the difference should be kind of the same. Because what does France and Paris, how are they related? Well, Paris is the capital of France. And what is Berlin in Germany? Berlin is the capital of Germany. So the difference of these two vectors should be the same, which encodes the semantic meaning that these are capitals. One of my favorite examples is that if you were to use ChatGPT and you were to vectorize the word king, vectorize the word queen, and then you were to vectorize the words uncle and aunt. What's the difference between a king and a queen? Gender. What's the difference between uncle and aunt? Gender, right? So if you were to subtract these word pairs, you would see their vectors are exactly the same. So why is this important? This is important because when you are building a model that predicts the next word, you want to make sure that your model generalizes very well. Now, how are you going to do that? Our models last time were not general at all, right? So for example, we even had some like letters in here like Q followed by J that we had seen 0 times in the training database. A model that is generalized is a model that even if it hasn't seen anything at training time, it's able to predict it properly at test time. So for example, for ChatGPT, I can come up with a random sequence of words that ChatGPT has likely never seen before. Right? Like let's say for example I start writing a poem and this poem, ChatGPT is trained on the internet. If I come up with a new poem from scratch, it's very likely that ChatGPT has never seen that sequence of words on the internet somewhere before. So how is ChatGPT still able to produce a response? Well, that's because the model is generalized. When it learned, when it trained on its data, it didn't simply train on the order of the words. It trained on the semantic meaning of the words. So what that means is that, for example, when we go back to this paper over here, when we learned the joint probability distribution of the cat is walking in the bedroom, our model should implicitly learn every time we see the word cat, we shouldn't just update for the word cat. We should update for the word dog too. For example, whenever we see data that relates to the word bedroom, right? Our gradients should not only update the embeddings for the word bedroom, they should also update the embeddings for the word room. So this is the key insight that Bengio came up with in this paper, which is that when you are training probabilistic language models, you don't want to only update that one column of, okay, these are the tokens that we saw in this particular order. You want to make sure that it's not discrete random variables, different words, but rather when I learn more information about one word, it changes the vectors of all the other words that are related to that word. Okay, Fazan, did that make sense? I think that got a little bit tricky to say, but does that make sense how during training time, we don't only want to learn the order of words, we want to learn their semantic meaning. Is that good?
Yes.
Okay, awesome. What that's going to lead us in a state with is that Bengio basically shows, Bengio does the same thing where he tries to train a model that's, in this case, it's a trigram model. So there's 3 words that, and again, he's working on the word level. We're working on the character level. So he's trying to, for example, predict, the cat in the hat, right? And he's going to look at the, cat, and in as his 3 input words. His context has, remember, context size 3. And he's trying to predict that next letter. So the cat in should then give the. And then cat in the should then give hat, right? But he's telling us that if we train a model that does this in a trigram fashion, and we're a little bit careful about the way that we train our model, we can end up with a model that doesn't only predict the next word, it also predicts word embeddings. And when we predict word embeddings, we've done something amazing. We figured out not just what words are most likely to come next after a sequence of words, we figured out what words in the English language are more similar, should be clustered together, and what words are more different. And that's important because then when we do our gradients and we update our model, if, for example, we find an update to the word bedroom, we're also going to implicitly update words like room, living room, drawing room, right? So words that are similar in meaning, but aren't that exactual word. So how can you determine the semantic meaning of a word? You can't, other than taking tons of sentences and seeing, okay, the word bedroom was frequently in a similar sentence or similar paragraph as the word room, right? So when you kind of see these sequences of words over and over and over again, you'll realize that, for example, walking and running are usually closer together whenever we have these paragraphs and or we have our training data than are words like walking and fighting, right? So that's the best that we're able to do right now is that we train on sequences of tokens. In this case, our tokens are words. And whenever similar tokens are in the same sentence, we say they're kind of related. Okay. That was like a 10,000-foot approach to word embedding. I'm going to come back to this paper later after we kind of implement key pieces. But the real thing you just have to take away right now is that we're building an n-gram model. We're building a neural network that takes in, let's say word one, word two, word three. It has a hidden layer. It computes our logits. If you guys remember what logits are from last time, they're like log counts. We perform a softmax, and finally we end up with a probability distribution for based off of these three words, what word is most likely to come next. And the only key thing here is before we go into that hidden layer, we need to make sure that we take our input token and we do a word embedding. So is that clear so far if it's on this picture? Does everything kind of make sense at this point? And feel free to ask any questions about this picture.
Yeah, can you explain the picture like what's going on in?
Sure. So this is the model that we're attempting to implement today. It's an n-gram model that has a word embedding right off the beginning. So Faizan, can you see my mouse?
Yeah.
Yeah. So the first thing that we do is we take in an index for a given word, right? So for example, in our vocabulary, A is one, B is two, C is three. You with me so far? So we have indices. Those indices go into a lookup table. That lookup table is called a word embedding or a token embedding, right? So basically, we're going to take a character like A or B or C, and we're going to get an embedding. An embedding is just a vector. A vector is a collection of numbers. So for example, for A, we might get like 1, 2. And for B, we might get like 5, 6. And for Q, we might get like 7, 8. Now, we know that like letters don't encode too much meaning. But if we were to do this with words, we would realize that the vector for the word bedroom would end up very similar as the vector for the word room. Okay, so you're with me so far, Faizan. The first step, we take a given token, we look up in our lookup table, which in this case is called C, to get our embedding vector. Is that good? Okay, so now we have, for our trigram, we have three input tokens. We generated the word to vector. We have their embedding vectors. We're going to chuck that through a neural network, and we're going to ask it, help me figure out the probability of the next word to come out. Does that make sense?
Yeah.
That's it, right? So that middle thing that you see right here and tan H, that's our hidden layer. So last time we did a single layer neural network. This time we're going to do a two-layer network. This is our first layer. That's what we call it hidden. And then finally our output layer. Our output layer, it has to have an output dimension of 27. Can anyone tell me why that is? 27 possible characters. There you go, right? So same thing for Bengio. His output dimension was 17,000 because he was dealing with words and he picked a subset of 17,000 words. So his model would predict the probabilities of the next word, and that final vector would have to be 27,000, sorry, 17,000 in length, i.e., the probability of each next word to come. Our case is a little bit simpler. We just have a final vector that's of dimension 27 because that's all the possible characters so far. Sweet. Faizan, does this kind of make sense? It's a neural net. The only difference between this and our previous neural nets is that this one is two layers as opposed to one layer. And instead of training it on the actual index, instead of training it on like a one-hot encoding, which is what we did last time, we're training it on an embedding. An embedding is just a random vector that we have in between. Make sense?
Yeah.
Okay, cool. Let's kind of jump into it. So, the last thing I just wanted to say is just review on what softmax is. If you guys remember last time, It's really difficult for neural nets to predict probabilities. Why is that? Probabilities have two rules. Probabilities sum up to one, and probabilities are never negative. This is really difficult to get neural nets to behave, right? Like I can do the math proof for you guys later, but basically, like we can talk about this in questions afterwards. But neural nets don't really understand when you're doing like gradient descent that, okay, I need to make sure that my final output sums to one. That constraint is just too difficult for neural nets to deal with. So remember last time we worked backwards. We said, okay, fine. Let's not make the neural net predict probabilities. Let's make the neural net predict the counts table. If you guys remember the counts table from here. Okay, neural nets can predict counts. And once we have counts, it's really easy to go to probability, right? Sum up all the counts. Each count gets divided by its sum. Boom, that's a probability distribution. Okay, cool. The only tweak that we made to that last time was instead of trying to get the model to predict counts, we just said, okay, we're going to have the model predict log counts. It's just a mathematical simplification. Once we deal in terms of logarithms, it just makes the math way easier. So now if our model is predicting log counts and we apply the softmax function, which basically does e to the log counts, so that goes away. We're left with counts. We normalize. We get our probability distribution. Now finally we're able to determine what's the probability of the next token. You with me, Fazan? Softmax, this is all a review from last time.
Yes.
Okay, sweet. Now let's go to coding. Let's have some fun. All right, we're going to import Torch. We are going to take our words data set. So if you guys remember last time, words is basically a file that has 32,000 words in it. Emma, Olivia, Ava, Isabella, these seem to be the most popular words. And these are basically, like just baby names, right? We're going to go ahead and build a vocabulary of characters and mapping to and from integers. So let's say, for example, what are all the characters here? Let's take a set of basically, if I were to join literally every single word in this data set, I would be left with, let's say, cars, right? And then if I were to turn that into a list, and then if I were to sort that, you would realize, oh my God, there are 26 letters in the English alphabet, right? Same as last time, we're going to have a mapping string to integer. Again, guys, this is all review. This is like literally copy pasted code from last time. So I'm not going to, explain it too much in detail. But S to I is a mapping that says that A is the first letter in the English alphabet, while Z is the 26th. I to S is the exact flip of that. So basically, for each S comma I in S2I items, we're going to basically flip those two right there. So now if I print ITOS, you'll see the first letter is A. It's just a flip, right? So this is just going to be really helpful for us going forward. If you guys just want to copy this code, the vocab size is going to be the length of ITOS. So remember, there's 26. Oh, wait, no, there should be 27 because I forgot the special token. The special token either comes at the start of a word or the end of a word. So this word, for example, Emma, right over here, it's EMMA. Our model shouldn't see that. Our model should see dot Emma dot because dot represents either start or end. That way, if our model predicts an end token, like a dot, we know that, okay, we've reached the end of the word, right? So we need to make sure that our vocab size is not 26, it is 27 because S2I is 0. Boom. Okay, awesome. S2I and ITOS are both dictionaries. That's correct. Okay. Let's kind of go ahead and just print ITOS, and I'm going to print vocab size so you guys can see. And hopefully, Fazan, you're coding alongside me, or maybe you're just watching. Yeah, both is good. I'm going to do something kind of interesting. Last time, for example, when it came to coming up with Emma, I had this little handy dandy thing right here. Just one second. Let me scroll. So much scrolling there. So much code that we wrote last time that I really have to scroll. You see right here, S, the start token, was followed by E, then M, then M, then A, then M, then A, then A, then N token. Now, I replaced start and end token with a dot this time, but this is basically our bigrams. I want to now do trigrams, all right? So let's see, how are we going to do trigrams? Well, let's just say that our trigram has 3 input characters, and it's going to have 1 output. That's our X and our Y. Context. This is going to be our context window, right? So this is our first time seeing context windows in real life. In this case, previously our context window was just 1 character. Now it's going to be 3. Let's, for example, use the word you hang, right? Yuheng is a name, and let's add the dot character at the end. And let's kind of just iterate one by one through this one. So let's say the n-gram is just an empty string so far. So I want to build the n-grams as we go along. So what this is basically going to do is I'm going to iterate through my context. And for every single character, I'm going to slowly pluck a character from the name and I'm going to dump that into my context. So what that looks like is that my context is going to be sliding over one element at a time. And then I'm going to grab the actual character right here. Okay, this is kind of ugly to look at, but let me get a little bit of print lines right here, and you guys can understand what the hell I'm talking about. But you'll see this code. Uh, semicolon right there. Okay. What I've done is I've written a little bit of code that will basically make this rolling window of characters, right? So previously we would have just done, Y leads to U and U leads to H and H leads to E, one character at a time. But Fazan, do you see how kind of this time, because we have a trigram approach, we want to have three stop or special characters, as in the complete beginning of a word. Okay, we want to predict Y, right? And then, for example, when we've only seen one letter, which is Y, we want to predict U. And when we've seen Y and U, H, and so on. Does this make sense, Fazan?
Yes.
Okay, awesome. I want to do this now, just not for the word you hang, but I want to do it for the entire data set. I'm going to copy paste some code. It's basically exactly similar to what we've done before, but I'm just going to make it generalized. So I'm going to set the block size as a variable. It's going to be 3 right now. And let's just look at this, for example, the first 5 words, right? So Emma, for example, we have three dots. The first letter here is E. For Olivia, the first letter was O, right? We're kind of doing the same thing. The nice thing here is now I can set this dynamically. So instead of instead of 3, let's do 6, right? So now I have 6 characters. You can see that, for example, my context window is so large that the names are not even filling them up, except, for example, for Isabella, which is long enough that, and this is, I think, really powerful because previously for like a bigram model or for a trigram model, I'm only looking at like one character at a time. For a hexgram model, for Isabella, I can basically see like almost the entire name when I'm trying to figure out what token comes next, right? So I'm getting a lot of context here. We're going to go through this later. Bengio ends up realizing that trigram was the model that had the most power. So we're going to keep block size to 3, just as he did. And we can kind of change that later. But basically, let's just do some PyTorch review again really quickly. So you'll see X and Y. So X is basically, this is each of my inputs. So I, for example, have, what's it called? A 32 predictions that I have right here. So there's 32 rows right here. You can see, for example, that first row is special character, special character, special character, right? And then Y, for example, is the index of the letter that is to be predicted that comes next, right? So 5, for example, if I were to do ITOS, this should be E, because E is the first letter of Emma, right? So this is my training data. Particularly, it's my input data and it's my predictions that I should be making, right? Awesome. Let's write a neural network that takes these X's, where the X, the input data, is, my context window, and based off my context window, makes an embedding for each of my characters, and then finally predicts Y. Fizan, are you with me so far?
Yeah.
Okay, awesome. Sweet. So remember from the paper, we have this image that says the first thing that we do is we take a given token and we generate a character embedding, right? So I'm going to make my character embedding matrix right here. So my character embedding matrix, let's say there are 27 letters in my vocabulary. And now we have to have an embedding dimension, right? So if, for example, let's say, for example, I think a ChatGPT, I think its embedding dimension is like of size like 5,000 or something like that. Basically, if I'm going to convert a character into a vector, right? I need to have a dimension for my vector, right? So you know how last time I said, like, if the vector for, let's say king is like 1, 2, 3 and queen is 4, 5, 6, that means that basically there's 3 numbers that is in that vector. So for now, we're going to start basic. I'm going to have each of my character embeddings just be a vector of length 2, right? So for example, if I do ITOS of 5, that's E. If I were to take this and then put that index basically into the character embedding, you'll see that the character embedding for the character E is this vector. right? For zero, zero is the special character, the dot character. Okay, this is the vector. 27 is the letter Z. This is the character embedding. Oops, I meant to say 26. My bad, 26. 20, the 26th letter of the English alphabet, Z, that's the character embedding right there. Okay, boom. So now we've generated our character embeddings. I want to just do something like really quickly and just let you guys know an interesting optimization. Going forward, we're just going to index into the character embedding. We're going to literally just use bracket notation. But I just want to show you guys something really quickly. If you guys remember last time, we weren't doing character embeddings. We were doing something called one-hot encoding. So if you remember, one-hot encoding is basically where I have, 27 zeros, like I said last time, and one of them is going to be flicked one. And this vector represents that actual character, right? So for example, let's do f dot one hot of 5. Let's say the number of classes in this case is 27. This is going to error because the first element needs to be a tensor. Everything in PyTorch has to be a tensor. Boom, that is the character embedding last time for last class for the character E, right? So this is the big improvement that we're making is that we're not using one-hot encoding. We're just using character embeddings. I want to show you something kind of cool though. If I were to take this vector, which is 1 by 27, let's just call, and if I were to multiply this by C, I would basically expect that this is the exact same thing as indexing into the embedding vector. So if I do C bracket 5, I can either do this or I can multiply my one-hot embedding by the character embedding matrix. So I don't actually need to use the index operation in Python. I can just do character matrix. Let's take a look at that. This will, oh, it'll fail. Why will it fail? Well, let's just do really quickly. The D type of this is int64, and the D type of the character embeddings is float32. Remember, whenever you work in PyTorch, the types have to match. So before we multiply these two, we have to do a cast, not float64, float. Okay, now we get a vector. And just to show you guys that one more time, if I were to use the index operator in Python, the index operator for the character 5, I get the exact same tensor. Okay, so the point that I'm just trying to teach you guys is that either we can think about this picture as indexing into a table where that table is the word embedding table, or we can kind of just think about this as a three-layer neural network, not a two-layer, a three-layer neural network whose first layer is the same for all the inputs here. And it's basically the word embeddings. We're going to come back to this when we do our GPT lecture, but that's just a little a thing to keep in mind. Don't worry about it if that got too confusing, because for the purpose of this lecture, we're just going to keep doing indexing. But I was just trying to teach you all that multiplying a one-hot encoded vector by a word embedding is the same thing as indexing into it. You with me so far, Fizan?
Yeah.
Cool. Let's keep going. So, like I said, C of 5, this is the character embedding for ITOS of 5 is E, right? So this is the character embedding for the letter E. I want to show you guys a cool thing that we can do in PyTorch. So in PyTorch, we can index into tensors using indices. We can actually index multiple indices at a time. So I can, oops, I need to pass a list. So now what this will do is that this is a tensor in the character embedding matrix for row 6, row 7, row 8. PyTorch is so cool, I can even do like row 8 a bunch of times, right? So PyTorch has really great support for indexing. But remember, our input matrix, which is X, it has a shape 32 by 3, right? So what we'd love to do is that input matrix, which basically the 32 represents all the different data points that we see, right? That like EMM leads to A. That's each of our trigrams. And then the first dimension is each one of our individual characters. We'd like to be able to index using X into C to end up with a matrix that gives us the word embedding for everything we've seen so far, right? So how am I going to do that? Well, you won't believe it. you can literally just do C bracket X. Whoa, okay, that's kind of crazy. What the hell did that do? Let's first look at the shape to understand it. So we took in, remember, C has a shape of, um, one second, C has a shape of 27 by 2. It's the character embeddings for each of our characters. And X has a shape of 32 by 3. That second dimension is 3 because we're doing trigrams. When I indexed 32 by 3 into this matrix, what I ended up with was for each of my 32 examples, for each of those trigrams, I want those characters. And each of those three characters, I get 2, which is the dimension of the embedding. So I basically end up with a three-dimensional tensor. Fazan, does that make sense?
Yeah.
Okay, and just to prove to you that everything is the same, let me go ahead and go in the original data X. If I were to do the 13th example, and if I were to take the final character in the trigram, right? So that's A, right? If you remember, if I were to do ITOS of this, I'm going to get, oh, oops, sorry. I have to do dot item. Ah, yeah, it's A, right? So if I were to do x of 13 comma 2, the 13th example, the final character was character A, which has index 1, right? If I were to then pass in, go to C and do C bracket 1, that's my character embedding. Or if I just, index the entirety of X to begin with, and then go to the 13th example and the second token, I see the exact same thing. So the point that I'm trying to just get you to understand is that if I can basically just do very easily C bracket X, I end up with this tensor that's 32 examples. Each of the examples is a trigram. Each of the characters in the trigram has dimension of size 2, which is the word embedding. Okay, cool. So these are embeddings. Let's go ahead and store that in a variable called emb. Awesome. Now, let's go ahead and make our first neural net. So if you guys remember this, this is an image that I showed on lecture one. Kazan, do you kind of remember this thing, what this is? What is this?
It's it represents like the neuron.
It's a single neuron in a neural network. And a neural network is composed of a layer of these, right? And then multiple layers is what we call a multiple layer perceptron or MLP, right? And if you remember, guys, a neuron is basically something that just takes a bunch of inputs, it multiplies them by a weight, adds a bias, which is like trigger happiness, and then goes ahead and applies the activation function. Again, guys, a lot of this is review, but I'm just saying this over and over again so we build up that comfortability. Okay, the inputs to this layer are three characters. It's a trigram, and each character is embedded as a 2D vector. So obviously 3 times 2 is 6. So I need to make sure that my layer 1, my W1 right here is going to be input of size 6, right? Because remember, for each one of my 32 examples, I have a 3 by 2 matrix. Each one of my tokens has a dimensionality of 2. So I'm just multiplying these two to say that my first weights matrix is going to take 6 inputs at the synapse, multiply each of those by weights, and then remember, a weight matrix asks the question, how many neurons do you want? Well, I can pick however many neurons I want, right? That's totally up to me. That's the hidden layer. I'm just going to pick 100 as the hidden layer to kind of go on. When I have 100 when I have 100 neurons, I'm gonna have 100 of these little boxes right here. So 100 of these inner products, if you guys remember from linear algebra. And I have to add a bias to this. So when I add my bias, I need to make sure that it is of size 100, right? I have 100 neurons and I have 100 biases. Cool. Let's just make sure that the math is going to work here. Um, Oh, wait, actually, no, we have a problem. I can't just naively take C bracket X and multiply it by, I can't just bracket take my embedding and multiply it by my weight. Why is that? Well, look at this. The embedding is of size 32 actually, hold on, this is a little bit wrong right here. This is C of capital X. The embedding is of size 32 by 3 by 2, right? And my matrix is of size 6 by 100. So none of our dimensions are aligning here, right? So I need to make sure that I fix that problem first. So why don't I say, okay, let me concatenate these together. If you guys can understand what's going on, each one of my trigrams has 3 tokens. Each of those tokens as an embedding. That's of dimension 2. So I have 2, 2, 2. I have 6 inputs to my neuron in total. Right now, this is not working because the shapes are like really ugly, right? This 3 by 2, we have to concatenate that together in order to multiply it by my neuron in my weights matrix. So let's just go ahead and do that. I'm going to use torch.cat, which is a function that's going to load. Oh, I need to search up PyTorch, torch.cat. Torch.cat is a function that allows us to take different vectors, concatenate them together. So we can, last time we actually used this, if you guys remember, to vertically stack vectors together. We can also, in this case, horizontally stack vectors together. So what we want to do is we want to say, okay, basically, let's take the embedding matrix. Let's grab all of the rows. Let's grab that first column, and then let's grab, all of the embeddings. Let me just grab the shape right there, right? And I want to do this for the first column, the second column, the third column, right? So basically, if I can take, again, the columns in this case represent my characters. If I can just stack those horizontally, then I'll end up with a matrix that's not 32 by 3 by 2. It'll be 32 by 6. And then, of course, I can multiply by weights. I'm going through this exercise so you guys get more comfortable with PyTorch, basically, right? So how do I do that? If I do torch.cat of basically a list of these, right? Um, let's see what the shape of this is. I messed up my parentheses. I need to have a close bracket. It's 96 by 2. Okay, whoa, 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 what happened here? I had a bunch of 32 by 2. I had a bunch of basically 3 by 2. Um, actually, excuse me. We ended up vertically concatenating. That's not what we want to do, right? So instead of taking each of those examples and getting each of their tokens and horizontally concatenating, because we need to give, for example, for each given input, right? For each given trigram, we want to have those 6 inputs, each one of those embeddings. We actually vertically concatenate. So let me just change dim equal to 1. Boom. Now it's 32 by 6. Now I can multiply this by my weight just fine, right? So this is called torch.cat, right? It allows us to concatenate vectors together. Now, you'll notice this is really freaking annoying. One reason why this is annoying is because let's imagine that we weren't dealing with trigrams, but we were dealing with pentagrams, right? So our embedding matrix would basically be a bunch of random weights that would not be 32 by 3 by 2. They would be 32 by 5 by 2. And so what we'd have to do is, going forward in our model, instead of grabbing column 1, column 2, column 3, we'd have to basically grab 5 columns, concatenate them, and then we'd end up with 32 by 10, and our layers could go on from there. So I want to like hopefully give you guys some, peace of mind to know that PyTorch creators were not that stupid. They made a function called unbind that's basically going to do exactly this. That's going to take our 32 by 3 by 2, each one of our trigrams, and instead of representing the trigram as a 3 by 2 matrix, it's going to just squash that together to six dimensions right there. So we can do torch.unbind of the embedding with dimension 1. What unbind does, let's do PyTorch, torch.unbind. Let's go to the docs. You'll see right here that unbind returns a tuple of the dimension, right? So if I have the default dimension is 0, you'll see we get 1, 2, 3, 4, 5, 6, 7, 8, 9, right? I'm actually going to take that example. Let's take this example and just print it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. If I change the dimension to be equal to 1, you'll now see 147, 258, 369, right? So now we're getting columns instead of rows, and we get a tuple of these tensors. So let's do exactly that. Let's do torch.unbind. Let's take the embedding and let's do dimension 1, which is going to be our columns. Now this is that same list that we were kind of generating last time. And now if I do torch.cat of this, we're basically good to go, right? So that's our 96 by 2 shape right here. Does that make sense? We're just doing some PyTorch manipulation of tensors right here. Is that good for them?
Yeah.
Any questions on what unbind or why are we concatenating? Does it make sense why we have to concatenate?
I guess can you explain?
Yes. So just one last time. We're building the first layer of our neural net. Our first layer is basically has six inputs. Fizan, do you know why we have six inputs to our neuron?
Because you have two, uh, you're embedding a shape of two for three letters.
Exactly. We have a trigram. Each one of our characters is a vector of length 2. So we need to make sure that our neuron, see this neuron, for example, has three inputs. Our neuron should have six inputs, uh, three characters, two embeddings for each of them. Okay, so you understand why we have six. You understand why we have 100, right? This is just our hidden layer. This is the number of neurons that I want to go ahead and fire. So we're gonna make 100 copies of this cell right here. You with me so far?
Yeah.
Okay, so the problem that I was showing them was that if I did the embedding multiplied by that matrix, it failed. And the reason it failed is because the embedding is of shape 32 by 3 by 2. So if you try to multiply something that's 32 by 3 by 2 by something that's 6 by 100, it doesn't work, right? So Faizan, how do we solve this problem? What needs to happen so the dimensions align?
You have to you're doing like destructuring the
Exactly. So what should the shape of my embedding matrix be? If anyone wants to type it, just one more time. What should the shape of my embedding matrix be when I'm multiplying this? Yes, it should be 32 by 6, right? 32 examples. And if my inner dimension is 6, again, that's the number of. Does that make sense? Why, Faizan? Previously, I had a 32 by 3 by 2, and this will not multiply mathematically with a 6 by 100. So I just need to multiply these two, and end up with a 32 by 6. Does that make sense?
yeah.
Okay. And the thing that I was explaining is the way that you can do that is that a 32 by 3 by 2 is like a rectangular prism, right? Each, rectangle represents a given trigram. And that rectangle is of length 3 by 2, right? And I just want to squash that to be not 32 by 3 by 2, but 32 by 6. And the way that I ended up doing that in this case was I grabbed each one of those columns, right? So this represents column 1, or column 1, column 2, column 3. And when I concatenated them together, I ended up with 32 examples and the concatenation of each one of those character embeddings. Does that make sense for them? Okay, awesome. Aditya said, is 100 an arbitrary choice? Yes, 100 is the dimension of our hidden layer. It's a hyperparameter. We can adjust it to be whatever the hell we want, right? So we'll keep it just 100, just simple right now. Okay, is that good, Faizan?
Yeah.
So torch.unbind is just a really simple way of saying what I just said, which is if I do torch.unbind, that gives me all of it basically gives me a tuple of all of my columns. So I'm going to dimension equals 1. That's my columns. I'm going to do embedding, right? These are tensors that have all of my columns. This is column 1, column 2, column 3. And then when I do a torch.cat, it's going to go ahead and give me a 32 by 6. So, sorry, I need torch.cat in the column dimension. There we go. 32 by 6. Does that make sense, Faizan?
Yeah.
Cool. This is extremely inefficient. What this is doing unbind, which creates three new tensors, and then it's doing a cat, which is doing a fourth tensor. So just to manipulate one piece of data, we ended up making four intermediate tensors. This is really bad, right? Going forward, we want to make sure that whenever we manipulate tensors, we reuse the same data as much as we can. Let me give you a really simple example. Let me give you torch.a range of 18. Fizan, you're with me, right?
Yeah.
Okay. This is a 18 by 1. It's an 18 by 1 vector, right? It has a shape 18 right there is the size. Pretty simple. What's really interesting is that there's this function called view that allows me to think about this same data, but in separate shapes. So for example, if I did a dot view of 9 by 2, oh, hey, look at that. It took my same data and it turned it into a 9 by 2 matrix. I can even turn it into a cube, right? So I can do, actually, let me change this to 27, right? Because 27, 3 cubed is 27, right? So I can do 8 of you. I can either do like 9 by 3. Wait, no. Run this cell. run this cell, right? Or I can do 3 by 3 by 3. Boom, look at that. There's my cube. Do you see that, Faizan? It's a tensor cube. But what's really interesting is that if I were to a dot storage, the data itself is still the same. A dot storage represents the actual data. So even though I made all these different views, it didn't make any new data. There was no copying, moving, creating. All that changes when you do a view is the metadata changes. Again, guys, this is going to be super important. Whenever we're manipulating tensors, we need to make sure that we don't inadvertently create new tensors because in machine learning, our tensors are massive, right? We're going to be working with, for example, hidden layers that are going to be of the size like 10 or 50,000. And we're going to have neural networks that are like hundreds of layers large, right? GPT-5 has 1 trillion parameters, right? That's crazy. Imagine doing gradient descent on that, right? It takes forever. We need to make sure that we minimize our total runtime as much as we can. So that's why we're going to use views. Views manipulate not the stored data, but the metadata about storage offset, strides, and shapes. If anyone is interested in this, I'm going to drop a link in the chat, which is also in your completed code. There's a cool blog about PyTorch internals that basically explains, okay, what the hell actually is a tensor? And the answer to that question is a tensor is just a collection of numbers that's just like 0 through 8, 0 through 26, and it's different views that represent the metadata. Okay, cool. Let's go ahead and go back to our embedding. We just want to have a different view. We don't need to like make an entirely new matrix. So let's just do that. Let's just tell PyTorch, yo, I don't want 32 by 3 by 2. I want 32 by 6. Wow. Okay, Saad, you took us on such a long detour to tell us that PyTorch had literally the exact same thing. And I just wanted to show you that yes, it is the same. So if I were to take that previous thing we were doing, where we were calling torch.unbind, we were grabbing the columns, we were concatenating them together. If I just set that equal to m.view, this is how you do element-wise comparison. You can see it's literally the exact same thing. All right, so you guys hopefully now believe me that m.view is the best way and the fastest way of turning our embedding matrix that was previously 32 by 3 by 2 into 32 by 6, right? So you'll see literally the data is exactly the same. Element-wise, it's the same. All right, cool. Let's move on. Any questions there, Faizan?
No.
Okay, now let's go ahead and do the first layer. I'm gonna just take a look on time. Hopefully, we're gonna end at 5:30. I have no idea though. Let's say our hidden layer is a view of 32 by 6. We're going to multiply by our weights matrix and we're going to add our biases, right? This is, what's it called? This is a single layer, a very simple single layer neural network, right? I just want to do one super quick thing. I don't like that we've hard coded the dimension right here because right now we're at 32 examples, but in the future we're going to train on our entire data set, which is going to be like, I don't know, like 28,000 or something like that. So let's just do m dot shape of 0. That's the exact same thing, right? Actually, one cool thing is PyTorch is so smart that anytime you have, for example, the final dimension, you can just put -1 as the dimension size, and PyTorch will infer that, okay, if this thing was previously 32 by 3 by 2, and Saad wants to reshape it into something whose second dimension is 6, process of elimination, it must be the case that this is 32. So that's just a cool PyTorch thing. You might be confused if you ever read some PyTorch code and you saw like dimension -1 all over the place. You might have been curious what that means. It's just PyTorch being smart. Cool. So we figured out how to make our first layer more efficient. Previously, torch.cat was making new memory. Now we are reusing our same input vectors, and only at inference time are we changing up the metadata in order to do our matrix multiplication. Right? Cool. We just glossed over one super quick thing. When I added the biases, you guys might be curious, Saad, this matrix multiplication, if I were to grab this thing right here, it has a shape of 32 by 100, right? 32 examples that each went through 100 neurons, right? How the hell did you add a 32 by 100 to a 1 by 100? That doesn't make any sense to me, Saad. Remember, last time we talked about broadcasting semantics. The way that PyTorch does this internally is that it lines up each of our vectors right padded. So in this case, it's going to say, okay, I want to add W1, which is 32 by 100, and I want to add B1, which is just of size 100. And the way that broadcasting works is that it says, okay, starting with the far right-hand side, do each of the elements match? So 100 and 100 is the same. Okay, good. Obviously, if my biases vector was not 100, it was 50, I can show you right now that's going to error super, super quickly, right? So let me show you that really quickly. If I were to take this 32 by 100 vector, and if I were to add it to torch.random of, let's say, 50, that's going to fail, right? So it needs to match dimensions, okay? Perfect. So these dimensions match. And remember, in broadcasting semantics, when we don't have a dimension, like we don't have it here in that spot, we fill it with a 1. And you might be thinking, Assad, 1 and 32 are obviously different. So PyTorch has a rule. Whenever a dimension does not align, error, unless one of the dimensions is 1, right? So in this case, when one of the dimensions is 1, we are going to duplicate or make enough copies of that vector, of that tensor, until the operation is sound. So what PyTorch does internally when it adds this result of W1 to B1 is that it makes 32 copies, right? So we had 30 by 100. We now will have 32 by 100, right? And those copies are going to be, what's it called? Row-wise copies, right? Because we're on that first element. So sometimes it's helpful to kind of go through this exercise, so you know that, okay, we have 100 elements that's being added to a matrix that's 32 by 100. So we have to make 32 copies, right? Awesome. Let's kind of keep going. So that's broadcasting semantics. Awesome. So now we have our hidden layer dot shape, and it's 32 by 100. Cool. Well, we know that we don't just want to become hidden forever. We want to now go to my second layer, which takes me to my output layer. So can anyone guess what should the shape of W2 be? So the hints that I'm going to give you so far is X, obviously, I'm going to give you X dot shape. I'm going to give you embedding dot shape, and I'm going to give you the hidden layer dot shape, which is really the hidden layer is the only thing that answers this question. What do you think the shape of my second layer should be? Okay, I got some guesses in the chat. Faizan, what do you think? So after we finish this second layer, sorry, after we finish this first layer, there will have been 100 neurons, right? Yeah. So what do you think the first dimension of our second layer should be? 100, obviously, right? Because again, in matrix multiplication, you always have to make sure that the dimensions match, right? So 100 is going to be the first one. If my hidden layer has an output dimension of 100, my final layer has to have an input dimension of 100. That makes sense? Yeah. So each neuron is going to be listening to 100 output neurons from the hidden dimension. So I'm going to do torch dot random of 100 by 27. Oh shit, I gave the answer. Sorry, I wasn't supposed to tell you the second dimension. The second dimension is 27 because there's 27 possible character outputs. But does that make sense, Fizan? Yeah. Okay, cool. Same thing. Okay, I'm gonna let you guess the biases. What does the bias have to be? How many biases do we need in a neural network? Well, if we go back to this, the bias is per neuron, right? So in the final layer, we're gonna do all those inner products. And each neuron is going to have a bias. So how many neurons do we end up with at the very end? At the very end, what are we doing at the end? We're trying to predict. Yeah, 27. 27, there you go. All right. Cool. All right, keep going. So now, remember, just like last time, I'm going to go to the previous code. We had this thing called logits. If you guys remember, logits are log counts. I've explained this 3 times already today, so I'm not going to explain it again. But logits is what we refer to as the output of a neural net right before we do softmax. Well, I said I wasn't going to explain it, and I explained it anyways. Okay, so our logits is our final thing, which is the result of the hidden layer multiplied by W2 added with the bias. Boom. That's my logits. What's logits.shape? It's 32 examples, and each of them have a log counts of the 27 different characters that it could be. Okay, cool. How do we turn this into a probability? Softmax. Softmax is we take our logits, we raise it e to the power of, I'm going to search up softmax on Google just to show you guys. There's the softmax function, right? So if our output layer is logits, log counts, if we raise it to the power of e, that log goes away and we end up with counts. And how do we normalize counts? Well, we sum by the total sum of all of those counts. So let me do that. Counts is logit.exp. The probability is going to be the normalized counts, which is counts.sum. And I need to make sure that I don't do this because this is counts.sum. I have to do one of that on dimension one, and this fails. Why does it fail? If you remember last time, we have this thing called keep dims. If you don't know why you do keep dims, please refer to the previous lecture. I'm not going to explain it again, but just trust me that this is, you have to make sure the dimension is not reduced. And the reason that the dimension is 1 over here is because remember, I have 32 examples, and I don't want to sum up like the column-wise. I want the row-wise sum. For the row-wise sum, I take a look for each one of my rows. I want to sum up the counts for all those examples and then divide. So because I want to normalize the rows and I don't want to normalize the columns, I use a 1 here. Guys, I'm trying to build up that comfortability with dimensions because I think it's like the hardest thing in PyTorch, just like getting a read on dimensions. But we can stop for questions in a little bit if that's confusing to anyone. Cool. So these are my probabilities. Awesome. So let's say, okay, how do I know it's a probability? If I take a given row of these probabilities, a given example, the sum should be 1. Okay. And again, if we don't do row-wise sum, if we do column-wise sum, you'll see we like break that, right? So again, the rows themselves have to sum. Keep dim. If you don't know why we use keep dim, go to last lecture and we'll explain it there. Cool. Each one of our probabilities for each one of our examples sums up to 1. Beautiful. Okay. The probabilities are like all wrong because we haven't trained our model yet, but we do have probabilities. How do we know our probabilities are wrong? Well, let's go to our ground truth. Our ground truth was our y. Remember, that's the token that we're trying to predict. I could do something really cool in PyTorch. I'm going to do torch.arange of 32. So this is for each one of our 32 examples, that's the index. And what I'm going to do is I'm going to index into prob. So I'm going to say, okay, so for each one of these ones, prob of 0 to 32, that's just going to grab literally all the probabilities. But for each one of the probabilities, for each of the 32 probabilities, I want the index of the character that was going to be predicted, right? So this will give me what does our current model see as the probabilities of each of the correct answers. So I'm going to write that one more time. So what we did over here, I'm just writing this in English so you guys can see it. For each row, we're going to grab the column that is correct. So what does correct mean? This tensor right over here, which we're going to call, let's say, Z. This tensor Z is a tensor of probabilities that our model predicted for each trigram. And specifically, it's the character it's the probability of the character that was actually seen. All right. Does this make sense? What's going on here, Faizan? What this line means? Okay. So again, we have our predicted probabilities, and for each one of the 32 examples, this Z tensor tells us what was the probability of the correct answer. What did our model think? And as you can see, it's mostly terrible, right? All of these are near 0. Is there even a single good one? This one is saying that the correct answer was 1%. This one was saying is literally, oh, wait, hold on. This one got it. Okay, this one somehow got it. Wait, is that right? 10 to the 0 is 1. Yeah, okay, this one like predicted it fully, but everything else is terrible, right? So it turns out that yes, having random weights does not help. But let's just calculate our loss right now, and then we'll do gradient descent, and then we'll go from some random weights to some weights that are ideally more sensible, right? So anyone remember, how do we calculate? What's a good loss function when you're dealing with probability distributions? Anyone remember? What's the loss function we used last time? Log loss. That's just close. Cross entropy is one way of calling it. What is cross entropy loss? Does that you remember? The loss function from last time?
Um, uh, Softmax.
Softmax is how we go from logits to probabilities. Once I have my probabilities, let's think about this intuitively, right? Let's say, for example, our model predicted E. Let's say we're doing the name Emma, right? Let's say we put a 50% chance of E, and a 50% chance of M, and a 50% chance of M, and a 50% chance of A. What's the probability that our model will predict Emma? It's 50% times 50% times 50% times 50%, right? Because modalities are multiplicative, right? For example, let's say, for example, our model predicted that E was going to come 100% of the time, and M was going to fall that 100%, and M was going to fall that 100%, and A was going to fall 100%. Do you see how the likelihood of our word is 100%? Because you just multiply all the probabilities together. Does that make sense?
Yeah.
Okay, so that's likelihood, right? But remember, likelihood was really difficult to deal with because doing the gradient descent on multiple things that you multiply is really hard. So if we're multiplying things really difficultly, what's a mathematical trick that we can use that can make the gradient easier? We can slap a log on it. Because if you have likelihood, which is the multiplication of several probabilities, and if I slap a log on it, log likelihood is just the sum of multiple probabilities. Does that make sense?
Mm.
Okay. And we know that we're going to do log likelihood. But remember last time we don't want to maximize log likelihood. We like to keep things in terms of minimize. So we're going to minimize the negative log likelihood. And we're going to do that for all of our samples. So we're going to average it. So our loss function is the mean negative log likelihood. This is a score that tells us how good or bad our model is. So let's calculate that. I'm going to take all my probabilities, same thing. I'm going to ask it, what is the probability of the actual correct answer? I'm going to log it. I'm going to do the average across all of the samples. I'm going to multiply it by -1, and that's my loss. And it's infinity. Um, it's infinity just because the numbers that I picked were like really, really unstable. I'll fix this later, right? Like we'll see. I can even kind of rerun everything just in a second with let's do another random weight. Let's do another random second layer right there, right? And then let's calculate another random second weight. There's my logits. And now if I do again, okay, it's nan. So we're just getting a really, really high loss that's so high that it's just not even numerically stable. So we're pretty terrible right now. Don't worry, I'll fix this later. We're going to obviously decrease the loss as we go on. Okay, cool. Let's go ahead and clean up this code so it's actually not spaghetti code. Cleaned up code. All right, if anyone is coding along, now is the time to a little bit pay attention because this is going to be the fun part. Okay, so let's go one more time. If I do our shapes, I have 32 examples of trigrams, and I have 32 tokens that those trigrams predict. Remember last time we used torch.generator? Generator is basically what makes sure that you and I have the exact same response because we're going to manually seed it. And the manual seed I'm going to pick is 214. I'm just going to copy and paste the manual seed in the chat. Um, ah, Okay, that's our generator. Now that we have seeded our generator, let's do random. So remember our dimensions of our character embedding is 27 characters in the English language, including a special token. And the embedding dimension is 2. And again, we have to use generator is equal to G. That's our character embedding. Then our first layer of the neural net was, remember, it takes in an input of size 6 because each of the characters of the trigram have an embedding dimension of 2. So 3 times 2 is 6. Our hidden layer was of size 100. Same thing, going to set that equal to G. Bias, remember our bias is the number of neurons that we have. Same thing for W2. Let's just copy this. So now the second layer of our neural net is going to be 100 input neurons that give us 27 neurons at the output, 27 activations, 27 biases. That is our model. what are all the parameters? The parameters are just a list of all of this. B1, W2, B2, right? So there you go. So if I were to basically tell you how many parameters does our model have, we have a pretty small model. Our model is 3,400 parameters. Again, for comparison, GPT-5 is 1 trillion parameters, right? So we have a really small model here. Now, let's go ahead and do a forward pass. Let's grab the embeddings on all of the data that we have. Let's go ahead and do, remember, embedding.view of -1, comma 6, right? So this is going to reshape our embedding. I'm doing this one more time just so we can all understand this. I'm going to add the bias. That's layer 1 of my neural net. But wait, I have to apply tan-h to that because that's my activation, right? And then to do my logits, I want to do my second layer, which is I do logits, sorry, the hidden layer times W2 plus the bias, right? And then finally, I need to calculate the softmax. The softmax is basically raising the logits to the power of E, normalizing, which is where we divide by the sum um, of the counts. And then finally, that loss function is right over here, where we take the probability, index into it what the correct answer is, do the log, do the mean, multiply by -1, and boom, that's my loss. Okay? So you can see right there, my loss is 15, right? Again, the reason it was infinity before was because we just had a random sequence of numbers where one number was so big that it just completely overpowered it. So that's why I picked this seed that the random numbers was going to work for my use case. Anyways, let's kind of keep going. These three lines, we're doing this over and over and over again. This softmax. Let's just use a function in PyTorch that does this for us called cross entropy loss. Cross entropy is basically taking your log counts and immediately calculating your loss, right? Right now, what we do is we take our logits, we turn it into softmax to get probabilities. We go from our probabilities to likelihood, and then finally we get our loss, right? So f dot cross entropy, this is a function that just does this for us. So let's do logits and y. You can see we get the exact same answer. I want to tell you guys, why do we want to replace our code? So let me grab this same code here. Mohammed, did you have a question? Okay, Faizan can answer that question in the chat. Why do you guys think that we want to use the cross-entropy function? Well, basically, again, we're creating a lot of intermediary tensors, right? The counts tensor, the probability tensor, the loss tensor. We don't have to have these two intermediaries. Instead, we can comment out these two lines of code here, right? I don't want these to be intermediary. And instead, I'm just going to set my loss to, even delete this, f dot cross entropy of logits and y. Okay, so why do we do this? The reason we do this is if you guys remember from the AutoGrad library that we implemented in lecture 1, sometimes when we are doing the backwards pass, we can have like mathematical optimizations that can make it really fast to the backwards pass. So right now, when we do our backwards pass on our loss, we have this like exponent, we have this division, we have this sum, we have this log, a mean, and a negative sign. Yes, we can do backpropagation of this, but our computational graph is so big. So one way of making this faster is, again, there are GPU kernels that PyTorch has implemented that mean that the backwards pass of cross entropy, instead of it being a bunch of mathematical operations, it's just one. And the reason I mentioned lecture 1 is if you guys remember lecture 1, we actually did exactly that, but not for cross entropy. We did it for tan-h. So if you guys remember for tan-h, we had like, we realized that, let me just pull this up right here. We realized that tan-h has a really nasty forward pass, but the backwards pass was really simple once you calculate this t value, right? So I'm trying to teach you guys, there's actually some mathematical optimizations you can do when you kind of think of these mathematical operations as kind of groups of operations, and then you do their backwards pass. It's much easier to do the gradient. So cross entropy is a much faster function. The other thing is it's more numerically stable. Okay, so let's say, for example, I had some logits. And let's say my logits were, I don't know, let's do a negative number like -2. Let's do 3, let's do 0, let's do 5. Right? So obviously, if I'm going to take this same code that calculates the counts, And in this case, counts.sum can just be like this because we're just one dimension. If I got the probabilities, it's pretty simple, right? So my probabilities, they look totally fine, right? If I were to replace this -2 with a -100 number, this goes to 0. Still, we're pretty numerically stable. What's interesting though is that if your logits don't have a very like really high negative numbers are totally fine because e to the power of a really high negative number is just almost 0. But e to the power of a really high positive number, that's not numerically stable. So instead of 5, if I use 50, or if I use, I don't know, 100, oh my God, I end up with nans. So that's what was happening before where you guys saw int for nan. When one of my numbers ends up being quite high in the positive direction, e to the power of 100 is so big that we experience a float overflow error, and PyTorch turns us into nans, right? So what PyTorch does under the hood in the cross entropy function is that instead of allowing this to happen, we realize that if we just normalize the vector, so if we just subtract whatever the maximum is here, so in this case, the maximum is 100, we're now once again numerically stable, right? So logits are something that you can shift linearly with no problem. So what PyTorch does under the hood for cross entropy is it first subtracts the logits by the maximum to ensure it's numerically stable. Okay, so all of that to say, I'm trying to convince you guys, please, 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 for the love of God, when you are machine learning engineers, do not implement cross entropy loss yourself. It's more efficient in the forward pass, it's more efficient in the backwards pass, and it's more numerically stable to use the actual PyTorch function. Does that make sense? Is that good, Fizan? Yeah. Cool. Let's implement the model ourselves. Sorry, now let's train our model. Okay, so now we're kind of getting to the fun part. I'm going to copy paste the same code from last time that just sets up all the random stuff right there. And then I'm going to do some forward pass code. So I'm going to grab the forward pass code right here. This is my embedding. These are my logits. Forward pass. And then I'm going to use my loss function, which is going to be the cross entropy loss right there. Let's now do the backwards pass. So remember, for backwards pass, we have to go through each of our parameters, and we have to call p.grad. Actually, sorry, we have to, yeah, set p.grad is equal to none, right? Remember, we did this last time with autograd as well. Set all the gradients to none. Once you've done that, then you can call the backwards a function on the final loss, and that will end up giving our gradient for each one of our parameters. And again, how do we update our parameters? Well, we just iterate through them. And then we say that, okay, p.data, let's crawl in the direction of the gradient. Well, this is called gradient ascent. We need to do gradient descent, so -1 times the gradient. And usually we multiply by a scaling factor, -0.1, that slowly crawls us towards the minimum of the function. Now let's go ahead and print our loss. All right, let's see what'll happen. And it errors. Okay, I knew this would happen. I'm going to give you guys a guess. What's one thing that I forgot to do that is very necessary in PyTorch, which is why this is erroring? There's some setting that I forgot to set. Is that any guesses? So you see it here. I got the forward pass. Then I have the backwards pass where I call loss.backwards. That's the line that's erroring. It does torch.autograd.backwards. Remember, we made our own autograd. And remember, we already set all of our gradients to none, so that's fine. But what's this error that we're getting? Element 0 of tensors does not require grad and does not have a grad function. Any idea? What's up? Optimizer. Not optimizer. We're not there yet. Remember how the whole point of the autograd library is to build this computational graph. But PyTorch is really smart. It's not going to build you a computational graph unless you really need it. So one thing that we forgot to do is we have to iterate through each of our parameters, and we have to set requires gradient to be true. If you guys remember, we actually did do this in lecture 1. That's it. Hunter got it right. Wait, great job, Hunter. You have to set requires grad to true. And now parameter is not defined because I spelled it wrong. Anticlimactic. There we go. Now we get a loss. Okay, so make sure, again, one more thing, whenever you're doing machine learning, always make sure that you tell PyTorch with these lines of code that, hey, I actually want you to keep track of the gradients. This is very memory expensive, but you need it when you're doing machine learning. All right, cool. Let's do the same forward pass, not once. Let's do it 1,000 times. And let's see our loss change in real time. I'm gonna do for I in range. 1,000. So now we're basically training a neural network. And now if I print it, there's my losses are going from 13 all the way down to like 0.25 is what it seems like we stabilize at. Let me just grab my logits, like the last logits that I calculated. If I were to calculate, okay, what is the maximum in, let's just do it in the column direction. I'm going to get for each of my examples, what's the maximum log count that I predicted? And one cool thing is that when I do the max function, it also gives me what's the index that's the maximum logit. And if I'm going to compare this to y, you'll see I'm kind of the same for some of them, but for like, do you guys see this? That for a lot of the entries, I'm the same, but for some of them, I'm different, right? So for example, you can see that the indices that we are predicting, for example, for the first token is almost always wrong. See how the first entry, so if you guys just remember, this is E. We predicted something wrong. This is M, this is M, this is M, this is A, right? It's predicting Emma correctly, right? And then when it goes to the first letter for the word Olivia, it gets it wrong, right? Maybe it's really hard to see it in these number fashion, but let me just show you this. The reason our model is not training that well and isn't able to achieve, a zero loss is because it's actually pretty confusing. Check this out. So you guys remember we're only training on 5 examples so far, right? So I'm going to go back to the code up here. I'm sorry, the five. ah, I'm gonna scroll all the way up. If you guys remember, these are the 5 words that we're training on so far. And each of the 5 words, there's 32 examples in total, 32 trigrams here, right? So I just pulled out the ones for the first letter. You can see that in our very small training data, there's 5 separate characters that could be the start. So basically, the model has like no idea what to do when it's given a start token, right? It says, okay, it could either be E, or it could be O, or it could be A, or it could be I, or it could be S. So it literally just gives you a uniform distribution over these first 5 characters. So how do we solve the problem? Well, let's train on the entirety of the data set, not just these 5 names, right? Hopefully that'll give us more information and a lower loss. All right, so let's go ahead and use the full data set. I'm going to copy paste the same code from last time. And now instead of doing, words of just bracket 5 as it was before, I'm going to do words, all of the words, right? So you're going to see right there, these are each of the words. Why am I printing this? It doesn't matter. I'm printing, do I have print line here somewhere? Yeah, I do. I'm printing the word right here. My bad. So this is the entirety of my data set, right? Let's go ahead and see my shapes of my X and Y. So you can see I have 228,000 names, 228,000, sorry, 228,000 not names. There's 220,000 trigrams, and each of those trigrams is a token that we're predicting, right? Now I'm going to go ahead and do the same thing. I'm going to grab the same 2-layer neural network. And now I'm going to, again, let's do just 10 times. I'm going to copy paste the same code up here. And I'm going to again, do the forward pass, backwards pass. I'm going to set a learning rate of 0.1, and I'm going to train it 10 times. And there you go. You can see that these are my losses. If I increase this, do you guys notice? Dang, this is really slow. Fizan, any guesses why this is so slow? Obviously, what changed here?
You're training the entire.
I'm training the entire data set. So what's happening is that when I'm doing a forward pass, I'm doing a forward pass on all 228,000 examples. Every single time, I'm forward passing all of it. And then my gradient is freaking massive. And then I'm doing backwards pass on a massive gradient. You can see this is really, really slow. Okay. So usually in machine learning, we don't do this. We don't do a forward pass on all of the examples at the same time. We do what's called batching. right? So, or mini batching as it's called. So we'll take a subset of the data set. And every time we do a forward pass, we're not going to train on the entirety of the data set. We're going to train on different subsets. So let's go ahead and implement that. Let's call this mini batching. There's this PyTorch function that's really useful here called torch.randomInteger. It will take a range between 0 to, let's say, 32, and it'll give me a random int. Oh, so this thing is still running. Wow, that was slow. Yeah, 1, 2, 3, 4, 5, 6, 7. See how slow that is, man. Now torch.randomInt, I need to give it a um, final size. So everything is in terms of tensor. So that final element is just how many random integers do you want? So I'm going to get a random integer from 0 to 32, right? Let's get 32 of these. So now I have 32 random integers that are between 0 to 32. Actually, we don't have 32 examples. We have like 228,000. So now I'm going to get 32 random indices that will index me into the row of my data. And now I'm going to grab the same model from before. I'm going to grab the same code that does the forward pass, but I'm going to add a small line right here that instead of doing a forward pass on the entirety of the data set, let's do it on a random subset of 32 rows, right? So now, again, let's change this to be 32, right? Let's do this code is the same, but now it's going to be 32 by 100. The logits are going to be 32 by 27. And now, oh my God, it's blazingly fast. It's much faster, right? So now I actually can much safely, I can train it on, let's say, 10,000 forward passes. All right, I'm going to let that run for just a second. So you can see we were a little bit faster there because we did a size 32. Wait, actually, guys, I'm so stupid. This is still equally as slow. I did not do anything with this index. I need to make sure that I index into it. So this X right here is of size 228,000. So I'm going to index into it right there. And then same thing for my Y, I'm going to index it right there. Now it should be much faster. I think. What did I do? I may have crashed it. Let me just try it one more time. So grab this, grab index.torch.randint. I'm going to make sure that when I'm in my character embeddings, I'm only grabbing the indexes that I think are necessary, right? 32 random indices. And then I also need to make sure that when I'm comparing with my final result, I'm only comparing to those actual final results. Okay, cool. Oh yeah, there we go. See how fast that was? It was instant. Oh my God. Yeah, way faster, right? It literally did 10,000 in just a second. Again, I'm going to show you guys this one more time. If I remove that, if I go to the old code and see how slow each forward pass is, it's like it took a couple seconds. If I do like 100 of these, like it takes like a second, maybe half a second. It's like coming out chunk by chunk, right? Kind of slow. And again, if I do a mini batch where I only do 32 in each forward pass, but a different 32, it's literally instant, right? So that's a technique that ML engineers use. What we're doing here is that in each forward pass, previously we were doing 228,000 examples. Now we're doing 32. So the dimension of our gradient is much smaller now, right? The first dimension is not 228K, it's 32. So yes, the quality of our gradient is worse. But now, because we're able to run so much faster, I don't have to do, for example, only 10 training steps. I can do like 100,000 and it's instant. So this is one of the trade-offs that ML engineers have to make. Do I want to have a higher quality gradient or do I want to have more training steps? And the answer to this is always dictated by your hardware. Cool. Let's keep going. I just got, these are just the losses for the mini batch itself. In order to calculate what the total loss is, I need to run the loss not on just a mini batch. I need to run it on the entirety of the data, which over here, this X is like 228K, right? This is 228K. 228K, right? There we go. So now my total loss is 2.3, right? We can go even lower. The way that we can go lower is we can adjust our learning rate. So I actually picked a pretty good learning rate to begin with. Let me just show you guys something else. Let's say I change the learning rate not from 0.1, but to be 1. you can see my loss is, once that finishes running, ah, too much ML training on my GPU, almost done. You know what, let me just kill it. Let me just run only for 10,000 steps. Okay, that was instant. So my loss is 2.45, right? So if I change the learning rate from, let's say, 1 to 0.1, my loss is from 2.45, it went up to 2.48, right? So these learning rates can also be tweaked to achieve a better loss. So I'm not going to go into this code. You guys have it in your completed thing. But what basically this section of code does is it tries 6 different learning rates. And for each of the learning rates, it makes a new neural network, sets the requires grad to true, does 1,000 training steps, and then it goes ahead and prints those losses. So let's go ahead and let that run for a couple seconds. You can see that as the learning rate is too high, our model, when it's doing gradient descent, you can imagine if there's like a parabola, it's just like pinging, like bouncing up and down. The goal of gradient descent is to take this like multi-dimensional loss surface and find the minimum. But what you do every time you do gradient descent is you kind of flick the ball, you flick the minimum, you flick your loss in the direction of the minimum. But if your learning rate is too high, you're just gonna be bouncing all over the place. So that's what's going on here. And again, if we make our learning rate too small, then it's just, a lot of computational effort, and you're just walking very, very small steps towards the minimum, but you're just going too slowly. So if I wanted to, get a lower loss here, I would need significantly more training steps, which again is increasing the amount of compute. So again, learning rate is a very important hyperparameter that kind of help you what to figure out what to do. I think a learning rate over here of about 0.1 or 0.05 seems to be optimal. So I'm just going to keep 0.1. One more thing I'm going to mention is that you can also have a variable learning rate. So in machine learning, sometimes what happens is that instead of having the same learning rate over time, usually if you begin your ML training with random weights, in the beginning, your loss is going to tank, right? So for example, I'm going to just do this same code, but this time what I'm going to do is I'm going to include a little bit of code that tracks step I and loss I. So this is going to be my losses for each of my steps. And I'm just going to plot this on matplotlib. Don't worry about this. But you can see right here, in the beginning, our loss is really, really high because we just have random weights. And then boom, immediately it jumps all the way to the bottom. So usually what you want to do is that for your first 1,000 steps, you want to have a really high loss, a really high learning rate, and you want to decay your learning rate over time. So one thing that people will do, for example, is I can have this code that says, okay, let's keep my learning rate as 0.1 if I'm in the first 10,000 steps of my training. But else, I'm going to set it to 0.01, right? So once I'm getting in those crevices of that loss function, that loss surface, then I'm going to move more slowly. All right, cool. I'm going to now introduce kind of the final concept for today, and then I'll let you guys. Actually, we have about 30 minutes left. Is that fine, Faizan?
Yeah.
Let's take a couple minute break. And how about at 5 p.m. we'll come back, we'll do the last 30 minutes, we'll do the fun part, which I kind of explain word embeddings, and we can see the model and this ngram model, we'll see the words that come out. But before we do that, why don't we take like a 3 or 4 minute break? So we'll recap at 5. And if anyone has any questions, Faizan, if you have any questions, now's a good time for a break. Yeah. So we'll take like a 3 or 4 minute break. I'm just going to look at some of the questions in the chat. Yeah, so Aditya had asked, the batch size has more of an influence on the time complexity than the number of batches. That's right. And the reason for that is when you have a larger and larger batch size, your computational graph is giant. So calculating the forward pass is obviously slower. You have more rows of matrix multiplication to do, right? And as we know, matrix multiplication is not like a linear time operation. It's like what, n cubed at least, right? You can do that point n to the power of 2.7 is like the fastest, right? But more than that, the backwards pass really does not scale well with size, right? You're building a giant computational graph. So when you have a larger and larger batch size. Now, compare that to just running the same steps over and over again. That doesn't trade off on times as badly, right? So it's also worse for memory, Aditya. That's another big thing. If I'm doing the same training with the same size parameters many, many more times, my memory is the same. But when, for example, I'm training on larger and larger batch sizes, I require more memory, right? So that'll slow me down, especially if it doesn't even fit into memory, for example. Yeah, cool. Any other questions, folks? Okay. Um, why do larger batch sizes result in better training? Larger batch sizes are good. It's not necessarily better training. Better training would be, for example, if I have a slightly smaller batch size, but I run for way more training steps. Better training is just whatever minimizes my loss. And as you can see, there's all these hyperparameters like learning rate and batch size and number of neurons and hidden layer size and dimensionality size and all these things that I've just been making up, right? That can result in better training. But to answer your question directly, why is larger batch size good? When I have a larger batch size, my gradient is of higher quality. There's more data that's informing which direction my gradient should go into. Literally, the dimension of my gradient is larger, right? So when I have a more defined gradient, because it's defined by more data, higher dimensions, I will walk more in the direction of the loss better. When I have a smaller dimension gradient that has seen less data, it may be the case that I walk in a wrong direction that ends up not decreasing my loss very well. Okay, for improving the performance, should we use optimizers like Atom or RMS Prob? Yes, you should use optimizers. Which one you should use is a question for another day. But basically, for those who don't know, what an optimizer does is that when we are basically doing our forward pass and we're computing the gradient, we're kind of computing the gradient of this multi-dimensional loss surface. And when we do gradient descent, we're trying to minimize, minimize, minimize our loss, right? So these loss surfaces are really bumpy, right? And frequently what happens is that you get caught in local minima, right? So one big problem with gradient descent is, let's say, for example, I'm going to go to Desmos. Wait, what happened? Uh, Kazan, can you guys still see my screen? No. Yeah. If I go to Desmos and I graph x to the fifth, x to the fourth minus x to the third plus x to the second, I'm just going to make some stuff up, minus x. And I'm going to put like random numbers. I'm going to put random numbers on this. What the heck? Put a random number there, put a random there. Okay. This is kind of ugly. Let's make this 7x to the fifth. Okay, this is like a totally random loss surface. Probably a pretty bad one. Okay. This is a bad example. Let me just search up loss surface. All right, this is a good example here. These are what loss surfaces for three-dimensional, like this is basically if we compress it down to three dimensionals. You can imagine that our loss is a point on this three-dimensional loss surface. And what gradient descent is doing is it's calculating the gradient, which is the direction of steepest descent. Now you can imagine if you were to take a ball and you were to drop that ball just somewhere here, then you might end up in these like local ridges or valleys. That's called a local minima. And even if you did gradient descent, you wouldn't be able to decrease your loss any more than that. What an optimizer like Atom does is skip connections is another thing that can make your model more convex. But just trust me, is that it takes this very irregular loss surface and it tries to make it convex. So that means that gradient descent has a much easier time getting to the minimum loss. Okay. Cool. Faizan, are we good to keep going? Yeah. Okay. The last thing I'm going to talk about before I show you the actual words that come out is someone else will get it. Okay. The training, validation, and test split. So one problem that we're having is we're having 228,000 pieces of data, and we're training on them, and we're basically just overfitting our data. Right. So even if we achieve a super, super low, like theoretically, we might even be able to achieve like a 0% loss on our training data set. right? But just because we have a 0% loss on our training data set doesn't mean that our model's actually any good. Because the model's not defined about what you see on training time, it's defined on what you see at test time. So frequently what can happen is that if you train your model for way too long, there's something known as the bias variance trade-off. So the bias variance trade-off basically says that once I've overfit past a certain point, the variance of my model, so as my model gets more and more complex, I can have a more and more high variance. And as I keep training, I can decrease my total error. But the problem is that my model will be less and less variant. And as I see more and more different types of data going forward, my model will have a difficult time generalizing. All of that is to say that you want to make sure that when you train on your training data and you make decisions about test time, validation time, anything like that, you don't overfit your training data. You don't make decisions that lead you to overfit. So one way that machine learning engineers do this is they split up their data into training, validation, and test, right? So we should only ever test the final loss on the test set. So the loss that's reported on a given like ML paper, that's the actual loss in the test set. But the validation, that's what we should basically run as we do batch by batch. Just one sec. Sorry about that, guys. Let me keep going. The actual loss that we should make decisions about hyperparameters on, that is on the validation set. So basically what I'm trying to say is we're going to split up our training split into 80%, 10%, 10%. That final 10%, that's our test split. We only ever calculate the loss once. And that's the final loss that we report, right? But then, for example, for validation, we're going to look at that internally to make decisions on what should our hyperparameters be, right? So I'm going to copy paste a lot of the same code that I did for building the data set. That's right here. So remember for building the data set, I have this like context thing. And if I wanted to, I could go ahead and like print out all of, the trigrams that we see. Should we use the confidence interval for validation? If you can just clarify what that question means. What do you mean by confidence interval? But I'm going to keep going. Basically, all right, just give me one second. Sorry about that, guys. Um, we are trying to split our data set into training, validation, and test set. This is going to do that for us. What this code does is it makes that same X and Y, and then it makes these XTrain, XDev, and XTest variables that basically we're just going to shuffle all the rows, and we're going to leave 80% of it for training, another 10% for validation, and another 10% for test. All right. Okay, so if our values fall into, for example, 95% confidence interval, can we validate the weights? Could you explain what you mean by confidence interval in that question? Maybe Fazan can answer that question later. I'm going to kind of just keep going. Now what we're going to do is we're going to take our same model and we're going to run it. This is the same code that I wrote up above. Same model, 30,000 steps. But this time, I'm going to run it on the training data set, right? And I'm going to do all my forwards and backwards passes only on the training data set, right? That's going to be, so this is going to run for 30,000 steps. Hopefully, that's going to be much faster. I'm also going to go ahead and plot uh, the loss right here. So ignore this like random line. I got to fix that later. But you can see the loss kind of tanks. And then what I want to do at the end is I want to take a look at my training loss, which is a result of running on my training data set, and then also my validation loss, which is on XDev, right? And you can see here that our training loss, which is what the model trained on, is almost the same as our validation loss. Now, there's a principle in machine learning that says that as you train more and more on the same training data, you should see your training loss like tank first, right? But your validation loss should hover slightly above. Now, why is that? Obviously, if you're training for more and more steps, you're going to be overfitting your model onto your training data. So what that would mean is that your loss for your validation data at some point, because you're only, fitting your model to the probability distribution of your training data, for validation, that validation loss should come down slightly, but it should basically stop coming down at a certain point. What our model is experiencing is our training loss is the exact same as our validation loss. So what that means is that we haven't overfit our model yet. There's more room for us to increase our training steps or even increase the size of the model. And that way we'll give the model additional functionality to overfit the training data. So before I do that, and before I teach you guys how to very quickly increase the size of your model, I want to show you are character embeddings. So remember, we started this lecture by talking about Bengio's paper. And Bengio's paper says that the first thing you do is you generate a character embedding. That's our C matrix. Well, I purposely kept our character embeddings as two-dimensional because I wanted to be able to plot them on a graph at the end. I want to show you what that looks like. So these are the character embeddings for our model. So our model thinks that, for example, in names, the letters G and P are related. So whenever, for example, we learn something about G or P, it should kind of adjust those weights accordingly. Q is like all the way at the end. Now, you know that in English, Q is a very rare letter, and Q is almost always preceded, is almost always followed by a U, right? So it makes sense that it's kind of off to its side. And then you can see all the vowels are kind of together. So I think this is like kind of cool. Our model has learned some semantic meaning about characters and we didn't tell it anything about characters. Again, you don't want to read too deep into this, especially because this is like a two-dimensional thing. And like I said, the better information is going to lie at higher dimensions. But let's go ahead and for 20 times, let's do the same thing we did last time. Remember how we made a multinomial function that would randomly sample from our probability distributions? Now let's see the names that come out of here. Hey, these names are more sensible. And you know what? If I even, I don't know, let's say increase my training time a bit more over here, let's wait for a little bit longer. So I'm going to build a data set for training time. I'm going to let this thing run for just a little bit longer. I want to make sure my computer doesn't crash. Is it running? Yes. Yeah, so that's running. That's gonna run for a couple minutes. We're gonna hopefully see basically these names are like decent quality, right? Like Correa, Ami, Heavy, Kimri, Rati, Salez, Aki, Dam, Pauline, right? Like again, these are not anyone's names, but you can kind of imagine Wazero, Jason. Jason kind of sounds like a name, right? So because our model has more context, because our model has more parameters, it's able to train on better and better names. Everything we do from here is just optimization, right? So now you guys understand how to implement the Bengio paper. You understand how to do character embeddings and how to relate tokens that previously you might have been thinking, like, how the frick am I going to teach a model that A, E, I, and U are like really close together because they're all vowels? Well, look, the model figured that out. You know what? It even, you know how like in elementary school they would say that Y is also a vowel, A, E, I, O, U, and Y. Look, our model even learned that Y is kind of like a vowel, right? So it's kind of cool. You can teach a model semantic understanding just by training a neural net to predict the next token. And this is going to be really important when we go to GPT-5. I'm going to let you guys stop for questions while I work on increasing the size of the model, which is going to make this thing even better. But go ahead, Fizan, do you have any questions? I'm going to write some code that's going to copy paste everything, and I'm just going to increase the size of the model. Um, is it the size of the training example in the batch or the entire batch size that ends up forming the context window? The context window here is 3. The context window is a trigram. It's any time that we predict the next character, we're looking at 3 at a time, right? The context window in Opus 4.6 is 1 million, right? So Opus 4.6 is capable of predicting the next token provided 1 million input tokens, right? So it has nothing to do with batch size. It has nothing to do with training time. Context size is a function of your model architecture, right? So our model architecture was trigram. Now we can change this, and I'm going to show this to you in just a second. I'm going to take this code over here. So let's grab the same X and Y. 182,000 examples. If you guys remember this code, previously, remember our hidden layer was 100. You guys remember right here, it was 100. This is what our code looked like previously. Now what I'm going to do is wherever it says 100, I'm going to replace that with hidden layer size, and I'm going to change this to 300, right? So now that hidden layer Remember, if I scroll all the way to the Bengio paper, this hidden layer was previously 100 neurons. Now I made it 300 neurons. Why did I do that? Remember, I told you guys my training loss and my validation loss were almost the same. We should expect that as we have more and more training steps, our training loss tanks because our model basically overfits and achieves an almost zero training loss. But our validation loss, which is on data that the model did not see at training time, has to be higher because how could the model overfit on something it didn't see? Right? So because my training loss was equal to my validation loss, I know that my model is struggling to predict even the training data. I need a bigger model, right? Okay, so I went ahead and trained that. Let's see what training and validation was I able to achieve now. 2.3. Wow, so I was on 2.4 before. Still, you can see one is 2.311, the other is 2.313. So now my training and my validation are like diverging. They're diverging by very little, which means I can still increase the size of my model. So now let's do that. Okay, so one parameter I can adjust is hidden layer size. Why don't we change the vocab dimension, right? So you know how previously my characters are 2D points, right? Like my embedding dimension was 2 dimensions. And I did that because I wanted to graph this for you all. Well, let's just increase the vocab dimension to not be 2 dimensional. Let's make it 10 dimensional. So everywhere where I see a 2, I need to change that to vocab dimension. So I'm just going to do that over here. Boom. So I just did a little find and replace right there. And anywhere there where there was previously a 2, see how there's like a 2 here, which represents, that was the size of my, what's called my embedding dimension. Now it's a 10, right? So this will be a 10 right here as well, right? So this is a vocab dimension. And then if you guys remember, previously, our first layer of the neural net had an input of size 6. That's because there's what's it called? A trigram has 3 characters, and each character had dimension 2. So we did 3 times 2, which was the input size of our first layer. Now we do the same thing. We do vocab dimension times 3. Cool. Now let's see what that looks like. I'm going to go ahead and calculate one more time the training and test loss. Hopefully I go down from 2.3. This thing is it's a way larger model, right? Jesus. I need to change this to be, remember, it's not 6 in the forward pass. It's vocab dimension times 3. Same thing here. Vocab dimension times 3. Wow, okay, so our loss went from 2.3, 2.36, 2.36. Then we increased the size of the model and it went down to 2.25, right? And again, guys, do you see our training loss and our validation loss are diverging? Our training loss is falling way quicker, 2.24. We're overfitting the model. So obviously it's performing very good on data it's never seen before, and it's performing relatively worse on data it's never seen. Wait, let me say it again. It's performing better on data it's seen before and worse on data it hasn't. So now the model is becoming less general. All right, finally, let's run this thing one more time. Boom. Wait, look at that. These names, what do you think about these names, Fazan? Delia, Neresia, Brandon. That's an actual name. Quinn, Eddie, Ab, Correa. Some of these, Tiana, some of these sound like names. And it's just predicting names from literally nothing, just a probability distribution, right? So if you want to compare that to the names that we predicted last time, it's like totally different, right? What was the name? Sexy was the name that we got last time. Uh, I'm trying to find it. There we go. Yeah, sexy Momo. So even the size of the name has changed because again, increasing context will dramatically perform your performance. So now if you guys search up Claude models and you're curious, why is everybody trying to increase what's the most important thing? The context window. This was previously 200K in Claude 4.5, and they upped it to 1 million. And that's the thing everybody cares about. I want Claude to be able to parse through more lines of code, and I want it to be able to understand it better, right? So that gives you more performance. Anyways, guys, I have a couple notes that I can share about the Bengio paper, but I'm gonna give Faizan the chance to ask any questions.
Yeah, I mean, okay, so why did Or how did Benjio come to the conclusion that three was the best kind of like size?
Yeah, he goes ahead and just tests a bunch of different things. So he tried trigrams, quadgram, pentagram. What's really interesting is that he actually realized that something called model ensembling is the best thing to do. So what Benchio does is that he will have his neural net predict the thing like off of whatever he has, and then he would take a trigram model and he would have it do the forward pass, and then he would take a weighted average of the two models, and that would be his probability. So this is something really interesting. Excuse me. So in his paper, if you guys read it, he mentions how he does ensembling with many, many different types of models. So he takes his model, which achieves the lowest loss, and he tries averaging that loss with a trigram model or a quadgram model or a pentagram model. Okay, now why might you want to do this? Our model is trying to learn the probability distributions, like the general meaning of words, right? Our model is not really caring about order as much anymore, right? If you notice, there's nothing in our model that distinguishes character one from character two from character three. Positionality is not encoded in the model, right? Is that clear why? If I were to scroll all the way up to this graph, do you see how, you see what I'm mousing? Oh, I'm gonna share my screen. Sorry. One second. Do you see how this character, and this character, their order is completely arbitrary? You could flip the characters within the trigram and it's the same result, right? That's what the model is not learning positionality. So what Benchio realized is that traditional trigram models do have positionality. So for example, if I do the president of, right? Our model is trying to understand the meaning of that. So if I do the president of, it's trying to think, okay, the meaning of president is like a leader of a country. So maybe a country should come next. But we know that on the internet, the phrase the president of the United States is like a very common phrase. It shows up over and over again. So because trigram models count the occurrences of a sequence of words, it's really useful to take our model and to do an average, a weighted average of this in a standard trigram model. And to answer your question, Fazan, the way that he knew trigram was best was he did this average with his model and a trigram model, his model and a quadgram model, his model and a pentagram model, and the trigram ensemble worked the best. This is a technique in machine learning called model ensembling, where basically you train 5 or 10 different models with different architectures. You have them all do a forward pass. You average their logits, and then you do the softmax to compute the probabilities. That ends up giving your model kind of different, ways or different pieces of understanding the same piece of data. Have you heard of random forests,
Yeah.
decision trees?
Yeah.
That's what random forests are. A decision tree is one model that makes one decision tree. And then if you put some randomization to it and make multiple decision trees, it turns out that having a majority of models vote on a result is more powerful than just one decision tree that's with more parameters. Yeah.
Will we get to boosting with the XGBoost?
I don't think it's in the lesson plan, but if you guys are particularly interested in
Maybe
it,
like
then we can try. Yeah.
more focused on like ensemble.
Yes. Yeah. We probably won't go too deep into ensembling. Why don't I maybe just walk you guys through the paper super quickly too? So if I'm gonna grab this and I'm gonna grab this. So whenever I read a paper, I want to show you guys my method. I put Claude on one side and I put the paper on the right side and I ask it to help me understand something piece by piece, right? So for example, for the abstract, abstracts are always super dense. A goal of statistical language modeling is to learn the joint probability function of sequences of words in a language. What the hell does that mean? I don't know, right? So I asked the thing to basically explain it to me, right? The thing that I really want you guys to take away from this paper is that Bengio is saying that we don't just want to predict sequences of words, right? That's what we were doing last week. Sequences of tokens, right? The problem with that is that if I have a sentence like the cat is walking in the bedroom that I see at training time, I learn almost nothing about that sentence if I have another sentence, a dog was running in the room. Again, human beings know that these two sentences are syntactically similar. The grammar is the same, subject, verb, prepositional phrase, right? The words are very similar, bedroom and room. But when you predict sequences of words, Bengio argues,
the model is not able to generalize and learn something about this sentence when presented at test time when it's seeing this at training time. So that's why Bengio has this whole mess where he makes his 2/3 layer neural network, where that first layer is not a traditional layer, it's a word embedding. And when he learns that word embedding, it means that whenever he encounters new data, he can say, okay, I've never seen the sequence of words, a dog is walking to the blank before, but I know that the vector for the word dog is really close to the vector for the word cat, right? And maybe the vector for the word bedroom is really close to the vector for the word room. So for that reason, you want to make sure that whatever your probability distribution is, it takes into account the vectors that are similar to it. So that's kind of the main idea from this paper. He also goes on and he talks about parallel processing. I was talking to my co-founder just now about how interesting this is to see about someone. He's basically begging for the existence of GPUs back in 2003, before they even existed. So yeah, but I'm kind of nerding out. Yeah. Okay, any other questions? Oh my God, some questions. Okay. So I guess it is not possible for the model to perform data on better on data it's never seen before and worse on data it has seen before. Yeah, no, that if Idrisu, if you ever see your validation loss is lower than your training loss, you have horribly messed up, right? Isn't this a technique used more in autoencoders? Autoencoders is this idea of regression where you're kind of training on the same data that you've seen over and over and over again. So, for example, an autoencoder will kind of build up context and pack that thing over and over again. We'll talk about that 2 weeks from now. Okay. Since the loss isn't going down by much, is it really worthwhile to increase the model size training complexity? Who said the loss is not going down by that much? Previously, it was from 2.5 to 2.2. That seems like it's not that big, but it's a high percentage change. But Aditya, it also depends on what your function for this thing is. This is a very, like, a model of size 100,000 weights is so small, right? Like it fits in memory, right? Like I can certainly with modern hardware, it's trivial to increase the model size up to 4 gigs, 4 to 8 gigs, right? So that's why, for example, if you search up, let's see, open source Quen models, the most popular model size is going to be, look at this, 1.8, 7B, 14B, and their biggest one is 72B. So Quen, for example, is a Chinese model open source. All of 3/4 of their biggest open source models, they're trying to make it so it fits in your RAM, right? So that's what's kind of dictating model sizes. Uh, yeah. Okay. Um, all right. Any other questions? Okay, cool. Yeah, guys, this was a lot of fun. Hopefully you guys enjoyed. And tune in next time where we learn about recurrent neural networks, RNNs, and that is going to set the stone for GPT. Yeah.
All right. Thank you everyone who joined. We're gonna be posting the workshop, or I mean the recording for this workshop on our website. So I'll just share the link here again. So you can watch the workshop and code alongside watching Saad talk as well. So hope you all have enjoyed the session and are looking forward to the next one as well. So take care everyone and have a great day.